Hello everyone and welcome to the STM32 Microcontroller tutorial number 4. In this tutorial, we explain how to generate pulse width modulation signals, or briefly PWM signals, by using STM32 microcontrollers. PWM signals are very important for mechatronics, robotics, and control applications. This is mainly because they are used as control signals for servo and DC motors. In this tutorial, we explain how to change a frequency and a duty cycle of PWM signals. In this tutorial series, we use the Nucleo 64 board with a product number given over here. However, everything explained in this video tutorial can be generalized to other board types as well as to other STM32 microcontrollers. Currently, we are generating a PWM output at this pin denoted by D7. The PWM signal is shown on the oscilloscope screen. The frequency of the generated PWM signals is approximately 10,000 Hz. The duty cycle is 30%. However, before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 500 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Also, I would like to mention the following. This video tutorial is made from the practice point of view. That is, I will not go deep into the theory of clocks or timers or microcontrollers. I will only present a few necessary formulas for you to implement and to generate a pulse width modulation signal. Okay, let's start with explanations. The pulse width modulation, or briefly PWM signal, is defined by the length of the pulse, denoted by S, the period of the PWM signal, denoted by TPWM, and Vmax. This is the maximal voltage value of the PWM signal. The frequency of the PWM signal is 1 over the period of the PWM signal. The duty cycle is defined as the ratio of S over T PWM. Here is the equation defining the duty cycle. In the STM32 development environment, we select the frequency of the PWM signal by using the three parameters and this equation. The frequency of the PWM signal is defined by FTC over KPS plus 1 multiplying KP plus 1, where FTC is the frequency of a timer clock of an STM32 microcontroller. Then KPS is the prescaler value and KP is the period value. The frequency of the timer clock, that is, the value of FTC, is usually expressed in megahertz. Usually, every STM32 microcontroller has a maximal prescribed value of FTC. However, we can still play with this parameter and we can select any value below the maximal value. Then, the prescaler value, KPS, is used to downscale the frequency of the timer clock. Another parameter that we can select is the period value denoted by KP. To summarize, by selecting FTC, KPS, and KP, we can select the frequency of the PWM signal. In the STM32 Cube IDE development environment, the period KP is called as auto reload registered and is abbreviated as ARR. That is, ARR is equal to KP. Then, in the STM32 Cube IDE development environment, the duty cycle is determined by this equation. It is equal to CCR over ARR plus 1, where CCR is the capture compare register. we select the value of CCR in the interval from 0 to ARR plus 1. That is, by selecting CCR, we can determine the duty cycle. Let us illustrate this with an example. Let us suppose that we want to generate a PWM signal with a frequency of 10,000 Hz. Then, let us suppose that the time clock frequency of our microcontroller is 84 MHz. Then, by using the prescaler value of KPS equal to 83 and the period of ARR equals to KP equals to 99, we obtain the desired frequency by using this formula. We can simply see if we substitute FTC, KPS, and KP, we will obtain 10,000 Hz. Next, we explain how to generate PWM signals. The first step is to open our development environment. Consequently, click on Start and search for STM32 Cube IDE. Open the development environment. Then click on File, click on New, and click on STM32 Project. As always, the first step is to select our board. So click on Board Selector, and over here you need to find your board. In my case, I'm using Nucleo 64, and if I click over here I will see all the available board. Now I need to search for the part number. Here's my board. Click on Next and give the name to your project. I will call it PWM1 and click on Finish and click on Yes. The next step is to select the pin that will be used to generate the PWM signals. That is, we need to select the output pin. However, here is the issue. These pin numbers are completely different from the pin numbers that you will see on your board. Consequently, we need to connect the pin numbers on our board with these pins. And the best way to do that is to search for the manual. So let's open our Google and let's search the board name. In my case, it's Nucleo 64446RE. Here it is. You can click over here, and then over here you need to search for manual. The easiest way to find the manual is to click on the top of the page on documentation and go down. Here you have two user manuals. You need to click on this one. You can save it and you can open it. Next, and here let's press Ctrl F and let's search for the board name. The name of my board is F446RE. However, in your case, the name might be different. And let's see all the matches. And here's the main graph. This graph is very important. These magenta letters actually represent the port names that are printed on your board. For example, over here I can see that D7 is actually PA8. And this is very important since the PA8 is the internal name for the name D7 of the port. And I will use this port and I will set it as the output port for generating the PWM signals. To repeat, I'm using PA8 and PA8 is actually the port D7 on the board. Next, let's go back to our development environment and let us explain how to properly initialize and adjust the parameters of our pins such that it can be used to generate the PWM signals. To remind you, we will be using PA8. So let's click on PA8. And over here you can see all the options. You can see GPIO input, GPIO output, and if you observe over here, you will see timer 1 channel 1. This means that we can actually assign a timer to this pin. Let me show you something before I actually click on timer 1 channel 1. If you, for example, select this pin, if you click on it, you will see that this pin can support some other timers, timer 14, timer 1, and timer 3, as well as timer 8. That is, some other pin will allow you to assign some other timers. However, in this tutorial, we'll be using this pin, and over here we can see only single timer. So let's click on that timer. And you can see that the pin became orange. This means that we need to make several other adjustments before the pin actually becomes green. When the pin becomes green, this means that this pin is actually enabled. To properly set our timer on this pin, we need to click on clock configuration. In this tutorial, we will be using the internal clock. Over here, HSI stands for high speed internal. Now, we can observe that the clock value is 84. Over here, we can adjust this value. However, we will keep 84 megahertz. So remember that value, 84 megahertz. This 84 megahertz is actually the value of FTC in this very important formula for selecting the frequency of the PWM signals. Again, FTC value is actually this value over here. Let's go back to pinout and configuration, and over here click on timers. Then click on timer 1, since this timer is actually attached to PA8. Click over here, and let's adjust our timer. First of all, the clock source should be internal clock. Channel 1 should be enabled, and here you need to select the proper value. Since we want to generate the pulse width modulation signals, we need to click on this option, PWM generation channel 1. Then we need to create a proper configuration. Consequently, expand this section. As we explained previously, to properly select the frequency of the pulse width modulation signal, we need to select the prescaler value, and we need to select the counter period, or the ARR parameter value. Let's go back to our formula. Here it is. Let us assume that we want to generate a pulse width modulation signal with a frequency of 10,000 Hz. Since the clock frequency is 84, the value of KPS should be 83, that is the scalar value should be 83, and the value of the period, that is the value of the ARR, should be 99. By substituting these values, we will obtain 10,000 Hz over here. So let's do that. First, we need to select the value of KPS, that is the prescaler value, to be equal to 83. So let's type over here 83. And the counter value, that is the ARR value, should be 99. Okay. If you scroll down this selection menu, you will see some other properties that you can adjust. However, in the interest of the brevity of this video tutorial, we will not play with other options. Okay, now let's look into this graph over here. And the first thing that you should observe is that our PA8 became completely green. This means that we have properly configured our output to generate the pulse width modulation signals. Next, we need to generate the code corresponding to these properties. To generate the C code, you need to click on Project, and you need to click on Generate Code, and click on Yes. Another approach for generating the code is to click over here. This development environment is smart enough to automatically bring the main C file. However, if for some reason the development environment doesn't open the main C file, you can find it by clicking on core, clicking on source, and inside of the source you can see the main.c. Let's analyze this file. First of all, let's find our int main function. Here it is. This is the core of our program, or better to say, an entry point. Now, let's see what's happening over here. We perform GPIO initialization, we also initialize our UART, and here it is. We actually initialize our timer. So let's try to find this function. If you scroll down, you'll find the function. And this function will actually code everything that we did graphically. If you now scroll down, you will see this structure, hTimer1. It selects the timer number, prescaler, sets the counter mode, sets the period, and some other properties. So what happened in between? When we actually clicked on project and generate code, the development environment automatically created this function corresponding to our graphical selections. This is very important to keep in mind. Instead of graphically selecting all these parameters, if you're proficient enough, you can automatically write this function. So there are several things to keep in mind over here. Our timer structure is hTimer1, and we will refer to this structure in our code. So let's go back to our int main function, starting from here, and let's look for comments over here. Here we can see user code begin in user code end. And in between these comments, let's add the code that will actually define the duty cycle of our pulse width modulation signal, and that will actually start the pulse width modulation signal. Now, let's go back to our formula for the duty cycle. Here it is. The duty cycle is CCR over ARR plus 1, where CCR is the capture compare register. ARR plus 1 is equal to 100. Consequently, if I want to generate a pulse width modulation signal with a duty cycle of 30%, CCR should be 30. Okay, so let's do that. Go back to our development environment, and over here I added two code lines. First, you need to specify the CCR value. It is equal to 30, and after you do that, you call this function from our HAL library, HAL timer PWM start. You specify the name of our timer structure, and you specify the timer channel. It is channel 1, and that's it. Simple as that. With two lines of code, you can actually generate the pulse width modulation signal. The first line of code will define the CCR parameter that in turn defines the duty cycle, and with this function you will actually start the timer. Next, click on project, and you need to build a project by clicking on build project. And over here, be careful and patient and see if you see some errors. Building finish, 0 errors, 0 warnings. Perfect. Now we are ready to upload the code to our board. To upload the code, click on this green play button. And let's keep the default parameters and click on OK. And after some time, the program will be actually downloaded, and you will get this message, download verified successfully. Now, if you have an oscilloscope in your room or in your lab, you should connect the oscilloscope to the pin D7. Another pin of the oscilloscope or the probe of the oscilloscope should be connected to the ground. That is, the ground of the probe should be connected to the ground of the board, and the signal of your oscilloscope should be connected to the pin D7. And you should look into your oscilloscope. Luckily, I can connect my oscilloscope to my computer. And here it is. If I click over here, the data acquisition will stop. Then, if I want to start my data acquisition, I will click over here on Auto. And after some time, you will see a real-time capture of our pulse width modulation signal. We can see that basically the period of our signal is 100 microseconds. 100 microseconds corresponds to the frequency of 10,000 Hertz, and that's precisely our desired frequency. We can also observe that approximate value of this pulse, that is the length of this pulse, let's see, is 20 plus 10, and that's 30. And if we divide 100 by 30, we will actually obtain 30% duty cycle. This means that this whole procedure for generating the pulse width modulation signals works perfectly. Next, let's play a little bit with the values of the parameters and let's change the value of the duty cycle. Go back to the development environment and let's change CCR to 80. 80 over 100 will correspond to 80%, and consequently this CCR value will generate a duty cycle of 80%. Let's verify that. First of all, click on Project and let's build our project. And finally, let's click here to run our project and to upload the code. Wait over here until you see download, verify successfully, and let's go back to our oscilloscope. And here it is. We can see that the length of the pulse is actually now 80 microseconds, and the period is 100, and 80 over 100 is actually 80%. This is a proof of principle that this whole procedure for generating pulse width modulation signals works perfectly. Okay, that's all for today, and see you in the next video tutorial.